Today, we're going to talk about the integral test and the P-series test. And these are two different tests that allow us to tell whether a series either converges or diverges, okay? So it's not going to, like the geometric series test tells us what the series would converge to. These don't, okay? These are just going to tell us, yes, this converges or it diverges. It doesn't tell us what it converges to, okay? So we'd have to do like partial sums in order to kind of figure out, okay, it's approaching this value, okay? So the first one is the integral test, okay? So if f, which represents a function, is positive, continuous, and decreasing for x greater than or equal to 1, and we're going to let our terms be like function values, okay? And I want to say this, okay? We got to show that it's positive. We got to show that it's continuous and decreasing. And the way we're going to do this is to show it's decreasing. We have to show that f prime is less than 0. So if the derivative is less than 0, that means it's decreasing. Okay, so that's how we're going to show the decreasing. We're going to look at the derivative. The other thing is, this doesn't have to be 1. I know we state 1 here, but it just has to be something. It can be something bigger than 1. So if it doesn't converge like from 1 to 5, but it starts to converge from 5 on, we could just jump to, okay, x is greater than or equal to 5. So we can do that here, okay? So we can change this slightly, okay? So what this series tests, if we meet these conditions that f is positive, continuous, and decreasing, all right, then this series and this improper integral from 1 to infinity f of x dx, they're either going to both converge or both diverge. So what we're going to do is we're going to rewrite this a sub n as a function and integrate it. And if we integrate it, we're going to know if that integral converges or diverges. So if the integral diverges, then we know this series diverges. If the integral converges, then the series will converge. They'll match. They'll do the same thing, okay? All right. So here we go. Here's this series, okay? Determine the convergence or divergence of the series n equals 1 to infinity of n over n squared plus 1. So what we're going to do is we're going to let f of x equal x over x squared plus 1. So that's going to be our function here that we're going to integrate. Okay, so the very first thing we got to do is, okay, we got to show that it's positive, okay? So if f is positive, okay, so if x is greater than or equal to 1, this numerator is going to be positive. This denominator we're going to square, which will, if it's negative, it's going to come out to be positive, but they're not negative, right? They're positive. So this is going to be positive, and then plus 1. Well, this is going to be positive. So yes, it's definitely going to be positive. Is it continuous? Yes, because there's no value here that's a real number value that would cause this denominator to be 0. That's what would cause it to be not continuous. All right. So the next thing we have to do is show that it's decreasing. Okay. So we got to find the derivative of this. So f prime of x would equal, and we're going to have to apply the quotient rule to this. So the derivative of x would be 1 times the bottom, which is x squared plus 1, minus the top times the derivative of the bottom, which would be 2x, all over x squared plus 1 squared. Okay, so cleaning up the top, this becomes x squared plus 1 and minus, and this would be 2x squared, all over x squared plus 1 squared. So cleaning this up a little bit more, we would wind up with negative x squared plus 1 over x squared plus 1 squared. Okay, but remember, our x's are greater than or equal to 1. So if they're greater than or equal to 1, this is going to be more than the x squared part is going to be more than this plus 1. So this is going to be negative. The numerator will wind up being negative. Our denominator, well, again, we're taking x squared and adding 1. That's going to be positive, and we're going to square it. So that's still going to be positive. So this denominator is always going to be positive, and the numerator is always going to be negative for x is greater than 1. Okay. So we've just shown, okay, f prime is going to be less than 0 for x greater than 1. So I'm saying greater than 1 because we can't include 1, because if we include one, that's not going to be negative. That's actually going to be 0, right? Because -1 squared, or negative, and then 1 squared would be 1. So this would cause it to be 0, which isn't negative. All right. So we can't use 1. So we're going to do greater than 1. And that's what I mean. Like, we can change this. Okay. So what this means is that f of x is positive. It's continuous. And decreasing for x greater than 1. Okay, so now what we're going to do is we're going to integrate. And because we're starting at 1, okay, we're going to integrate from 1 to infinity of our f of x, which is this x over x squared plus 1. Okay, so we're gonna have to change this to a limit, right? Because we can't have an infinity be an upper bound. Okay, so this is going to equal the limit as b approaches infinity of 1 to b of x over x squared plus 1 dx. Okay, I'm going to slide my paper up just a little bit so we can see this. All right. Now, we're going to need to use integration by substitution. So we're going to let u equal x squared plus 1, and du would be 2x dx. So I need a 2 here, so I also need to multiply by 1/2. So this is going to equal the limit as b approaches infinity of 1/2 the integral. Okay, and I'm not gonna change these two u values. Okay, I'm gonna change it back to 1 over 1 to b, and then this is gonna be 2x over x squared plus 1 dx, and that'd be the limit as b approaches infinity of 1/2 the integral of, and then this from 1 to b, and this would be u, and this would be du. So we have 1 over u du. I don't want to switch these to u values because I'm doing this limit as b approaches infinity. Okay, so that's why I don't want to switch them. Okay, so then that makes this equal to the limit as b approaches infinity of 1/2, and then the integral from 1 to b of 1 over u would be what I just messed up. Okay, natural log of the absolute value of u, right? But u is x squared plus 1, so absolute value of x squared plus 1. And then we want to evaluate this from 1 to b. Okay, so this is the limit as b approaches infinity of 1/2 times ln of the absolute value of b squared plus 1 minus 1/2 ln of the absolute value of 1 squared plus 1, which would be 2. I'm going to put parentheses around this. Okay, so what happens as b approaches infinity? Okay, so this is going to get bigger and bigger and bigger, right? Because b is going to infinity. So what you're taking the log of is getting bigger and bigger. And remember the natural log just keeps getting bigger and bigger and bigger and bigger. So this is getting, the natural log is getting bigger. Half of that's still going to get bigger, and it's always going to be bigger than this, right? So it's just going to go to infinity, all right? So this is equal to infinity, which tells us that the integral from 1 to infinity of x over x squared plus 1 dx diverges. Okay, so now what we know is that since the integral from 1 to infinity x over x squared plus 1 dx diverges, comma, the series n equals 1 to infinity of n over n squared plus 1 diverges. Because remember, whatever, they both do the same thing. So they're either both going to diverge or they're both going to converge, right? So this series diverges, and we have to state the test. So diverges by the integral test. Okay. And that's how you do these problems. That's how you apply the integral test. Okay. So we're going to have to take the derivative and see what's happening if the derivative is negative. Okay. And then we got to make this statement. Then you got to do the integral part of it. Okay. Then you find out, okay, that integral diverges. And then you got to state, okay, since this improper integral diverges, we know that the series also has to diverge. And how do we know that? By the integral test. Okay. And that's what we applied here. All right. Let's do another problem of these. So for this next problem, let's determine the convergence or divergence of the series sigma n equals 1 to infinity of 1 over n squared plus 1. So we're going to let f of x equal 1 over x squared plus 1. Okay, so we want to show that it's positive, okay, it's continuous, and it's decreasing. We got to show that. All right. Well, we don't have to show it at all, but you have to consider it. Okay. So is this positive? Okay. So the numerator is always going to be positive because it's 1. All right. The denominator is always going to be positive because remember, x is greater than or equal to 1. So when x is greater than or equal to 1, this is going to be positive, and we're going to add 1. So that's still going to be positive. So this is the fraction value is always going to be positive. It's continuous because there's no real number that you could square to cancel out adding 1, right? This would have to be -1. So yeah, it's going to be continuous. All right. There's no breaks in the graph. Okay. And now the last thing we need to really talk about is it decreasing, right? So you can tell if it's decreasing by taking the derivative. Okay. So I would say it'd be easier, instead of trying to apply the quotient rule right here, I would rewrite this as x squared plus 1 to the -1 power. I think that's just going to be a little bit easier to find the derivative. So f prime of x would be, so this would be -1 times x squared plus 1 to the -2 power times 2x. That winds up being -2x over x squared plus 1 squared. Okay, so the denominator here, okay, we're taking a number. Remember, again, x is greater than or equal to 1. Right? So if x is greater than or equal to 1, this is going to be positive. Well, when I square, it's going to be positive. So this denominator is always going to be positive. But for the numerator, x is always going to be greater than or equal to 1. Okay, but I'm multiplying by -2. That's going to cause the numerator to always be negative and the denominator to always be positive, right? So that's going to cause our derivative to be less than 0. It's going to cause our derivative to be negative. For x is greater than or equal to 1, that's going to be true. So we can say f of x is positive. It's continuous. And decreasing let's say for x greater than or equal to 1. Okay, so that means we can apply this integral test, right? So we're going to take the integral from 1 to infinity of our function, which is 1 over x squared plus 1 dx. Okay. And then what we need to do on this one is realize, well, we need to write this as a limit. Sorry about that. We need to write this as a limit. So limit as b approaches infinity of the integral from 1 to b of 1 over x squared plus 1 dx. And what we have to do here is we have to recognize, okay, this is the derivative of something. So you can't do u substitution. You can't do anything like that. You have to recognize this, okay? And what this is 1 over x squared plus 1 is the derivative of arctan, okay, or tan inverse. So that means this becomes the limit as b approaches infinity of, okay, tan inverse or arctan of x. And then we want to evaluate that from 1 to b. So this would equal the limit as b approaches infinity of arctan of b minus arctan of 1. Okay, so, all right, this is where it helps if you know arctan and the graph of arctan and this approaching infinity, the graph of arctan has two horizontal asymptotes, okay? It comes up like this, it comes like this. And here's a horizontal asymptote, and here's a horizontal asymptote. This one is at y equals pi over 2, and this one's at y is equal to negative pi over 2. Okay, so that means that as b approaches infinity, arctan, right? Arctan is going to get closer and closer and closer to pi over 2. So this becomes pi over 2 and arctan of 1. Now remember, this is the ratio, right? This is the ratio. And what do we get out? We get out an angle. So what's the ratio if the ratio is 1 here? Well, it's 1 over 1. Well, that's going to happen right here in the first quadrant. 1, 1, and you should recognize if those are the legs 1 and 1, right? Y over x, then this would be the square root of 2. That would make this angle pi over 4. So that means this is going to become pi over 2 minus pi over 4, or 2 pi over 4 minus pi over 4. And so this becomes pi over 2. Okay, so what does this tell us? This tells us that this integral converges, and it converges to this pi over 2. Now, this is really important. This is not what the series necessarily converges to. It's what the integral converges to, okay, which is different, all right? So, but we do know, since this one converges, we know our series is also going to converge, okay? So we know the integral from 1 to infinity of 1 over x squared plus 1 dx converges. And since, so here we go, since the integral from 1 to infinity of 1 over x squared plus 1 dx converges, since that one converges, the series n equals 1 to infinity of 1 over n squared plus 1 converges, because they're both going to do the same thing, by, and what allows us to say this? It's the integral test. So you always got to say these tests that we're using. And so that's an example of where we do the integral test and it doesn't, it tells us the series diverges. And here's one where it actually tells us it converges, okay? But once again, the integral converges to pi over 2, but that doesn't mean that this series converges to pi over 2, okay? All right. Okay, so let's talk about the p-series test. That's what we're going to talk about next. And it's actually, we need the integral test. I'm not going to go through all the proofs of these, but we actually need the integral test to show it's called the p-series test, okay, to show that why that one works. But I'm not going to get into all that, all right? We just have to be able to use this stuff, okay? So let's go to the next page. Okay, so now we're going to talk about the p-series and the p-series and also the harmonic series. The harmonic series is just a special p-series, okay? So what is a p-series? A series of the form that looks like this: n equals 1 to infinity of 1 over n to some power p. So this could be 2, this could be 3. It's a power, okay? So if it's a power, then this would be 1 over 1 to the p power plus 1 over 2 to the p power plus 1 over 3 to the p power. So if this was n cubed, this would be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, okay? If p was 5, then this would be 1 over 1 to the 5th plus 1 over 2 to the 5th. So this power is always the same for each term, right? It's just we're changing this n value, and we're starting at n equals 1, and we're going up by 1 each time, okay? So P is positive and constant, okay? So P is positive. So we can't have negative power series, okay, or negative P, all right? For P equals 1, this series would look like this, right? So our power would be 1, and that would look like this: 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7. That's called the harmonic series, okay? And then we're going to look at what's called the P series test. It's a very simple test. It's a very, very, very useful test, okay? And basically it's this, and it comes from integration, the integral test, that we know this is true, okay? So the P series, again, we said what it is, right? It's going to converge if our power is greater than 1. If this power right here is greater than 1, so 2, 3, 4, 3.5, any of those, okay, then we know it's going to converge. It's going to diverge if the power is between 0 and 1, and it could include 1. So that means the harmonic series diverges. And actually, when you get a harmonic series, you can just say, okay, this series diverges because it's a harmonic series. Okay, you can actually just say that. Or you could say, oh, it diverges because the P series test. Okay, so let's look at this one, okay? So here's the harmonic series right here. Sigma equals n equals 1 to infinity of 1 over n. We recognize that in this problem, our power is 1, okay? And so we can say since P equals 1 and 0 is less than P less than or equal to 1, what do we know? We know that the series diverges, okay? So by that, we know the series sigma n equals 1 to infinity of 1 over n, and we'd say diverges by the P series test. You're going to see in the next few days and weeks, okay, why this test is really, really important, okay? All right. You could also, an equivalent way of saying this is you could identify this as a harmonic series and say, okay, the series diverges because it's a harmonic series. You could say that, and it would be justified. Even on the AP exam, you could say that, okay? All right, so let's look at the next one. What's really nice about these P series is it's really quick and easy to show that it either converges or diverges. That's why they're going to be very useful, because we're going to do some things called the direct comparison test and the comparison test and the ratio test. There's a whole bunch of tests that we're going to do to see convergence. And when we do these comparisons, we're going to compare it to one of these that we know, okay? All right, so right here, we recognize, okay, P, in this case, my P is equal to 2. That's my power right there for n, okay? And so since P equals 2 and P is greater than 1, right? It's greater than 1. Okay, so we now know that this series n equals 1 to infinity of 1 over n squared. So when our power is greater than 1, we know that this series is going to converge. Okay, and so we say that series converges by the P series test. P stands for power. Okay. Right. And that's all you have to do. Okay. And that's how you show either converges or diverges using the P series test. Really quick and easy. Okay. Okay. So for this last example for today is we want to determine, again, the convergence or divergence of this series right here. Okay. So what's going to become hard is we're going to have a lot of different tests. And part of this is determining which test should we use in the particular situation. Okay. So P series is good if you have like n to some power, right? And we don't have that here. We have 1 over n ln of n, right? So we should also recognize that this isn't the geometric series, right? So we can't use the geometric series test, okay? So what else could we use? Well, I've taught you that integral test now, right? So this is a candidate. I would say this is a candidate to use the integral test to determine whether it converges or diverges, all right? So we're going to let f of x equal 1 over x ln of x. Now, to use the integral test, we have to determine that this is positive, that it's continuous, and also that it's decreasing. And we're going to use the derivative to show that it's decreasing. Okay. So is it positive? Okay. Well, notice we're not starting at 2 now, right? Or sorry, we're not starting at 1. We're starting at 2. Okay. So if we can't start at 1, because if we started at 1, then that would be 1 here, and ln of 1 would be 0. And so this would be 0, and then it wouldn't be continuous, and then we wouldn't be able to use the integral test, right? Because it's not, and we wouldn't have anything to use actually, right? We wouldn't be able to do it. So we're making this be 2, and it's gonna work, because if this is 2, ln of 2 is the natural logarithm function from 1 on is going to be above the x-axis. So this is going to be positive, and 1 is positive. So this whole thing is going to be positive. Okay. The only way it would be not continuous is if n was 0, but it's not, or if n was 1, because then that would make ln of 1 is 0. Okay. So those are the only two situations, but we're not starting at n equals 0, and we're not starting at n equals 1. We're actually starting at n equals 2, which is going to allow us to show that it's positive and it's continuous. Okay. So then the other thing we need to do is find the derivative. Okay. I actually started this problem just a little bit ago, and I stopped my recording because I didn't like the way I rewrote it to do the derivative. And I had done the derivative earlier just for practice. And so I realized what's better to write this is I originally wrote this as x to the negative 1 times ln of x, all of that raised to the negative 1. And I think it's easier if we do this. So this, I'm going to rewrite this as x times ln of x raised to the negative 1 power. Okay, that would be exactly the same as 1 over x ln of x. Okay, so I'm going to apply the chain rule, but then inside here, I have to apply the product rule for my derivative. Okay, so that makes f prime of x equal to negative 1 times x times ln of x raised to the negative 2. And now I got to apply the product rule to this inside function. So that would be 1 times ln of x plus, and then we'd have x times the derivative ln of x, which is 1 over x. Okay, so this makes negative 1. This is going to get switched to the bottom. So I have negative 1 over, and this bottom would be x times ln of x raised to the second power. And then this top, I'd have up here in the top, I'd have natural log of x plus 1. Now, remember, we're starting at 2, right? We're starting at 2. So if we put 2 in here, this is going to be positive, right? And if we keep putting 2, 3, 4, 5, right? If as x gets bigger and bigger and bigger, this is just going to stay positive, right? But we're multiplying by negative 1. So that's going to make the numerator negative. We're squaring here, right? And x is starting to, x is 2, then 3, 4, 5, and so on, right? So right here, both of these are going to be positive, but I'm squaring, so that's going to be positive. This denominator is always going to be positive. The numerator is always going to be negative when x is greater than or equal to 2. So we can say f of x is positive, continuous, and decreasing for x greater than or equal to 2. So we don't have to start at 1. We can start at some number further out. Okay, so that means this is a candidate for the integral test, right? We can use it. We have to meet these conditions. If it wasn't decreasing, or if it wasn't continuous, or if it wasn't positive, we wouldn't be able to use the integral test. And actually, at this point, we wouldn't have anything else to use, and we wouldn't be able to determine this at all. Okay. All right. So let's go and let's start writing our integral. Okay. So our integral, instead of starting at 1, because n is starting at 2, our integral is going to start at 2. So we're going to go 2 to infinity of 1 over x ln of x, and then dx. We're going to switch this to a limit. So the limit as b approaches infinity of the integral from 2 to b of 1 over x ln of x dx. Okay. All right, so here the decision, right? Like, how do we integrate this, right? So this isn't something we should recognize like the arctan one just a minute ago, but we could use substitution, right? So if we let u equal ln of x, and let me grab a different color. Hold on a second. I can tell I'm running out of ink in my red. All right, and so then the derivative of that du would be 1 over x dx. So you may not recognize this, but this is really equal to the limit as b approaches infinity. We have all the parts here, okay? 2 to b, and this would be 1 over ln of x times 1 over x times dx. And see, this whole thing right here becomes my du, right? And this is my u. So that makes this the limit as b approaches infinity of the integral from 2 to b of 1 over u du. So that makes this integral become the limit as b approaches infinity of, and so the integral of 1 over u would be ln of the absolute value of u, but u is ln of x. So this is ln of the absolute value of ln of x. All right. And we're going to evaluate that from 2 to b. That's equal to the limit as b approaches infinity of, all right, so here we go, ln of the absolute value of ln of b minus ln of the absolute value of ln of 2. All right, so let's talk about what's going on, because this is going to be a little tricky here. All right, so b is going to infinity, right? B is going to infinity. All right, if b is going to infinity, as your inputs get bigger and bigger and bigger, ln gets bigger and bigger and bigger, which becomes an input for this next ln, which gets bigger and bigger and bigger. So this whole thing is going to infinity minus, this is just a constant, right? So it's infinity minus number. Well, that's just still infinity. So that means this is equal to infinity, which tells us that this integral, this improper integral, the integral from 2 to infinity of 1 over x ln of x dx, which is equal to, well, equal to infinity, right? But that tells us that this integral diverges. And because we met the conditions for the integral test, right? And we used it to show that this diverges, that means the series has to diverge, okay? So we would write, since the integral from 2 to infinity of 1 over x ln of x dx diverges, the series sigma n equals 2 to infinity 1 over n ln of n also diverges by the integral test. Okay, and that's how you show that this series diverges using the integral test. Okay. All right, guys, that's it for today. That was kind of a little bit lengthy. All right. These are going to get a little more complicated. We're going to have more tests, and then what's going to be hard is like picking which test to use. All right. Okay, guys, that's it. Have a great day.